Environmental regulations should be based on technically sound and legally defensible data analyses that are interpreted using the best available science. This tutorial compares mathematical deterministic process models with stochastic statistical models to answer regulatory questions. The models used to support environmental regulations under conditions of uncertainty have not kept pace with our increased understanding of ecosystems and their responses to human industrial activities, nor to advances in statistics that fit the unique attributes of environmental data. The result is that environmental regulators lack the insight they need to make effective decisions under conditions of change and uncertainty. This tutorial examines 4 common deterministic models applied to aquatic ecosystems and compares them to advanced statistical models for supporting environmental regulatory decisions. Environmental regulatory science is used to assess proposed and existing projects and operations for compliance with environmental laws and statutes which require permits. There are 4 reasons why models are used by regulators to support their permitting decisions. 1. To quantify existing ecosystem components and relationships to understand existing ecosystem structure, function, and variability. 2. To forecast possible changes related to the project's activities. 3. To monitor the ecosystem and distinguish natural variabilities from anthropogenic ones. 4. To compare alternatives for restoring and maintaining desired future ecosystem conditions. When environmental regulations in the U.S. were first written, the most common models for analyzing natural ecosystems were mathematical, specifically deterministic models that describe ecosystem processes. Many of these models are still being used. Now that abundant computing power is widely available and statistical models appropriate for analysis of environmental data are abundant and available at no cost, they are the tools of choice for supporting environmental policies and regulations. Statistical models are fit to the available data, are based on sound and proven mathematics, and when model results are interpreted using established scientific theory, the results are technically sound and legally defensible. Statistical models quantify uncertainties in stochastic, that is highly variable, ecosystems, so results help regulators make decisions more quickly and with confidence that the decisions are justified. Deterministic mathematical models are sets of differential equations to define how ecosystem components change from one time step to the next time step. The model structure is applied to all ecosystems of that type rather than designed specifically for the one being modeled. The model structure is created using equations that express what is believed to be the relationships between a response variable and explanatory variables. Therefore, mathematical models require input data be fit to the fixed equations of the model. Often, these complex models require very large data sets as the input, which are costly in time and money, or not possible to acquire, so it's common to estimate or assume values for rates and constants. 4 mathematical deterministic models commonly used to inform operational, regulatory, and policy decisions are HSPF, Qual2E, Pittlake-Q, and BLM. The complexity and comprehensive inclusiveness of these models require very large amounts of data if they are to incorporate inherent natural variability. These models are great research tools to increase understanding of the mechanisms and dynamics of the systems they model, but they are inappropriate for operational, regulatory, or policy use because time and cost constraints limit the quantity of input data and because the output is determined by the structure of the equations. Most importantly, they do not correctly answer questions about ecosystem status, trends over space and time, or forecast future status. Hydrologic Simulation Program Fortran is one of the first environmental deterministic models. The model was developed in the early 1960s as the Stanford Watershed Model. In the 1970s, water quality processes were added. Development of a Fortran version incorporating several related models using software engineering design and development concepts was funded by the EPA in the late 1970s. Development continues under the U.S. Geological Survey. HSPF simulates hydrologic and associated water quality processes on pervious and impervious land surfaces, in streams, and in well-mixed impoundments that for extended periods of time. The model contains hundreds of process algorithms developed from theory, laboratory experiments, and empirical relations obtained from the instrumented watersheds. Dozens of data types are required as inputs to the model. HSPF uses continuous rainfall and other meteorological records to compute streamflow hydrographs and pollutographs. The model simulates interception of soil moisture, surface runoff, water recharge, dissolved oxygen, biochemical oxygen demand, or BOD, temperature, pesticides, fecal coliforms, sediment detachment and transport, sediment routing by particle size, channel routing, reservoir routing, constituent routing, pH, ammonia, nitrite, nitrate, organic nitrogen, orthophosphate, organic phosphorus, phytoplankton, and zooplankton. The model can be configured to simulate one or many pervious or impervious unit areas discharging to one of many river reaches or reservoirs. Frequency duration analysis can be done for every time series. Any time step from 1 minute to 1 day that is divisible into 1 day can be used. Any period from a few minutes to hundreds of years may be simulated. HSPF is generally used to assess the effects of land use change, reservoir operations, point or non-point treatment alterations, flow diversions, and etc. Programs available separately support data pre-processing and post-processing for statistical and graphical analyses of data saved in the watershed data management file. This image illustrates the USGS calibration parameters used to simulate stream flow from application of the HSPF model to mountainous basins containing coal mines in West Virginia. Data requirements include meteorologic records of precipitation and estimates of potential evapotranspiration for watershed simulation. Air temperature, dew point temperature, wind, and solar radiation are required for snowmelt. Air temperature, wind, solar radiation, humidity, cloud cover, tillage practice, point source, and or pesticide application may be required for water quality simulation. Physical measurements and related parameters are required to describe the land area, channels, and reservoirs. When data are not available, constants and rates need to be estimated by the user. Of course, many of these variables change at time scales of minutes to weeks. What then do needed model outputs represent? A second frequently used model is the USGS's Enhanced Stream Water Quality Model, Qual2E. This is a comprehensive one-dimensional stream water quality model. It simulates the major reactions of nutrient cycles, algal production, benthic and carbonaceous demand, atmospheric reaeration, and their effects on the dissolved oxygen balance. In addition, the model includes a heat balance for computation of temperature and mass balance for conservative minerals, coliform bacteria, and non-conservative constituents such as radioactive substances. This image illustrates the process modeled by the Qual2e stream water model. Qual2e is intended as a water quality planning tool for developing total maximum daily loads, TMDLs, and can also be used in conjunction with field sampling for identifying the magnitude and quality characteristics of non-point sources. Qual2e has been explicitly developed for steady flow and steady waste load conditions and is therefore a steady-state model, although temperature and algae reactions can vary on a diurnal basis. Although the core of the model has not changed since 1987, there have been some modifications to the interface and other associated tools to assist the users. The conceptual representation of a stream used in the Qual2e formulation is a stream reach that has been divided into a number of subreaches or computational elements equivalent to finite difference elements. For each computational element, a hydrologic balance in terms of flow, a heat balance in terms of temperature, and a materials balance in terms of concentration is written. Both advective and dispersive transports are considered in the mathematical materials balance. The model uses a finite difference solution of the advective dispersion mass transport and reaction equations, and it specifically uses a special steady-state implementation of an implicit backwards differential numerical scheme which gives the model an unconditional stability. Qual2e requires some degree of modeling sophistication and expertise on the part of a user. The user must supply more than 100 individual inputs, some of which require considerable judgment to estimate. The input data can be grouped into three categories: a stream-river system, global variables, and forcing functions. The first group, input data for the stream-river system, describes the stream system into a format the model can read. The general variables group describes the general simulation variables such as units, simulation type, water quality constituents, and some physical characteristics of the basin. The forcing function are user-specified inputs that drive the system being modeled. The input data values depend on the type of simulation and the number of state variables used. These are all process descriptions, not data descriptions. PitLake-Q couples the model CE Qual W2, a two-dimensional water quality and hydrodynamic model, and FrequentQC. The U.S. Geological Survey aqueous geochemical calculations modeled and adds new functionality to account for the pit lake requirements. It includes the most important processes in pit lakes. For example, several sources of acidity, such as erosion or release from submerged sediments and spatially distributed groundwater inflow. These help to represent pit lake conditions. Furthermore, PitLake-Q can account for the effects of water treatment on water quality. The two-dimensional model set up with one vertical and one horizontal dimension allows having sinks and sources with defined spatial location. This image illustrates the processes modeled by the PitLake-Q deterministic model. Pitley-Q models hydrodynamics, transport, heat exchange, wind impact, ice cover, tributary inflow, atmospheric exchanges of O2 and CO2, precipitation, evaporation, groundwater exchange, groundwater flow and transport, erosion, both mass transport and water quality impacts, algae and nutrients, chemical lake reactions, mineral precipitation, sediment release, deliberate treatment on defined spatial and temporal schedules, alkalinity of sinks and sources, coupling of all processes, and user process additions and modifications. The biotic ligand model, BLM, is a numerical model that couples chemical speciation calculations with toxicological information to predict toxicity of an aquatic metal on a particular species. This approach was proposed as an alternative to expensive toxicological testing, and the EPA incorporated the BLM into the 2007 revised freshwater aquatic life ambient quality criteria for copper. Research BLMs for silver, nickel, lead, and zinc are also available, and many other BLMs are under development. Current BLMs are limited to one metal, one organism in limited stream reach considerations. Although the BLM generally is an improvement over previous approaches to determining water quality criteria, there are several serious limitations in implementing the BLM, particularly at mined and mineralized sites. These challenges include historically incomplete data sets for BLM input parameters, especially dissolved organic carbon, or DOC. Several concerns about DOC, such as fractionization in iron and aluminum-rich systems, and differences in DOC quality that result in variations in metal binding affinities. Water quality parameters and resulting metal toxicity predictions that are temporally and spatially dependent. Additional influences on metal bioavailability, such as multiple metal toxicity, dietary metal toxicity, and competition among organisms or metals. Potential importance of metal interactions with solid or gas phases and or kinetically controlled reactions, and finally, the tolerance to metal toxicity observed for aquatic organisms living in areas with elevated metal concentrations. In 2015, the Oregon Department of Environmental Quality, ODEQ, conducted an analysis of the copper BLM in preparation for replacing the state's aquatic life water quality standard for copper. The BLM requires 11 input parameters to derive criteria based on site-specific water chemistry. Because of the number of model input parameters, a major objective of the ODEQ analysis was to evaluate methods to estimate variables from missing model inputs. A method for estimating geochemical ion concentration using specific conductance measurements was adopted. The agency also adopted an approach to simplify large geographic scales by combining EPA Level 3 ecoregions into 4 physiographic BLM assessment regions for evaluating potential regional estimates of BLM parameters or criteria where model data are insufficient or absent. Unfortunately, this doesn't fit the generally accepted definition of site-specific and causes model outputs to miss inherent natural variability. There were a limited number of locations and sampling events that had measured data for all the required BLM input parameters. Therefore, to derive BLM criteria, estimates of missing parameters will frequently be required. Also, ODEQ's analyses verified that BLM criteria calculations are most sensitive to dissolved organic carbon and pH. Consequently, estimating values for DOC or pH results in significant uncertainty in the accuracy of BLM criteria. The regulator's analysis indicates there are no routinely collected surrogate parameters that can be used to accurately estimate DOC or pH. The descriptions of the four mathematical models reveal common characteristics that should concern the regulated public, consultants, and attorneys who assist them in obtaining permits and demonstrating compliance, also to regulators and policymakers. For example, each requires extensive input data, a large number of variables, and many replicate values over time from each location. This requirement works for academic and government scientists who can devote the time and effort to obtain sufficient data for the model run to yield non-trivial results. But this does not work for a regulatory context where business needs and regulatory staff require decisions in short time frames with limited staff and available monies. Each of the mathematical models requires estimates or assumptions for missing data, and the spatial scales are likely to be too large or too small for regulatory decisions about a particular project or local population of fish. Each numeric model has a static structure, Qual2E's has not changed since 1987, to which highly variable data need to be fit. None of them quantify spatio-temporal variabilities which are found in all ecosystems, especially aquatic ones. Therefore, it is not surprising when it's discovered that model output does not match measurements and observations in the stream, river, lake, or reservoir of interest. Statistics can be considered the science of uncertainties because it is based on probabilities and how well a model fits the available data. Statistical models address concerns such as characterization of the data, estimates of the expected value, variance, skewness, etc., estimation of the probabilistic future behavior of a system based on past behavior, extrapolation or interpolation of data based on probability, error estimation of observations, or spectral analyses of data. Unlike deterministic models, the statistical model is fit to the existing data. Usually, the data analyst fits several such models and mathematically determines which one best fits the data. There are two main statistical paradigms or approaches, and each has a role in the analysis of environmental data. The frequentist paradigm is the most familiar because it is taught in all basic statistics courses as part of a science or business curriculum. This paradigm is based on the expected frequencies of values if the population is described by a specific probability distribution. There are two types of frequentist analysis: null hypothesis significant testing and information theoretic. The null hypothesis approach tests two hypotheses, the null and an alternative, and calculates the probability of observing the data or more extreme values if the null hypothesis is true. The alternative hypothesis is not actually tested. The standard acceptance threshold is 5%, the familiar p equals 0.05. Unless environmental data have been suitably transformed, the null hypothesis significance testing approach has limited use with environmental data. When the probability is greater than 0.05, the null hypothesis is not accepted, but only not rejected. The information theoretic approach uses maximum likelihood estimation, MLE, to evaluate which of multiple hypotheses is best fit by the data. The MLE approach provides greater flexibility than does the null hypothesis testing approach in analyzing environmental data. Neither type of frequency testing can answer questions about biological data, such as calculating the probability of a species being present at a habitat regardless of being observed there, or at any given site visit. The Bayesian paradigm incorporates existing knowledge into the prediction of future conditions. While this might seem counterintuitive or flaky, it is a robust approach well suited to many environmental data sets, particularly biological ones. Perhaps it is more easily accepted when we understand that we subjectively use this approach to make decisions about our actions. We fish and hunt where we have been successful in the past, and we select commuting routes and times to avoid congestion and delays we have experienced in the past. What Thomas Bayes did was to put this knowledge in a mathematical probability format. The first thing the environmental data analyst does with a data set is to describe and characterize it visually and numerically. Environmental data differ from business, financial, and social data that are often statistically analyzed. Therefore, environmental data characterization is needed to determine both what questions the data can answer and which model best fits the data. Geochemical data in water, sediments, soils, and rocks are continuous data with only positive concentration values that are not normally distributed. That is, the familiar bell-shaped curve cannot describe the distribution of possible values. Chemical concentrations cannot be less than 0, regardless of units of measure. Frequently have long tails on the right side from infrequent high values, and can have values below laboratory detection limits, which are called censored values. They also tend to be collected at irregular periods. Geochemical data represent parts of a whole which are expressed in the units used to describe their concentration in a medium, for example, milligrams per liter, or parts per million, or parts per billion, and similar types. The most useful visual characterization of geochemical data is the box and whisker plot, commonly called a box plot. This figure is a box plot of several hundred copper concentrations from each of two river systems, the Humboldt and Owyhee rivers in northeastern Nevada. There are 5 components in each box plot. The minimum and maximum values, which are the second and fourth quartiles, other than outliers more than 150% of the median values, represented by the whiskers, the short horizontal lines at the ends of the dotted vertical lines. The range of the middle 50% of values, the second and fourth quartiles, represented by the box. This is equivalent to 1 standard deviation in a normal distribution. The median concentration, the heavy horizontal line in the middle of the box, is equivalent to the mean value of a normal distribution. The open circles are outlying values that might or might not have significance. The thin horizontal line across the entire figure at 0.001 milligrams per liter is the analytical laboratory's method detection limit. Values below that line were not directly measured. They are censored. Box plots represent a full description and characterization of the data that is easily understood by all viewers. From a policy and regulatory perspective, the most visible differences in the two rivers raises the question of why they are so different. What explanatory variables cause the differences in copper concentrations in the two rivers, and do differences reflect inherent variability or anthropogenic influences? One very important characterization of environmental, chemical, and biological data sets is variability. Not only does understanding inherent natural variability enhance decisions about policy and regulations, it also identifies which class of statistical models are most likely to produce technically sound and legally defensible results. Statistical models are based on probability distributions, and there are many from which to select. Wikipedia lists 34 discrete probability distributions used for count and presence-absence data, and 106 continuous probability distributions, which are used for continuous data like geochemicals. Even more exist, and each has specific parameters and applicability to a wide range of data types and characteristics. This permits the most appropriate model to be fit to any available data set, unlike deterministic models that have fixed equations to which the data must be fit. There are two common types of environmental data: measured and nominal, or named. A broad range of statistical models for comparing environmental and forecasting changes and for comparing environments and forecasting changes are available to analyze these mixed effects data sets. Quantified and named data are used in environmental regulatory decision-making, ecotoxicology, and ecological risk assessments. Measured quantities of physical, chemical, and biological data are familiar to everyone and are used as response variables, also described as dependent variables, because they are dependent on explanatory or independent variables. Explanatory named variables can be important in understanding the difference in response variables. Common examples of nominal explanatory variables include season, soil type, stream name, and vegetation type. Both measured and nominal types are common in data applicable to the Clean Water Act, Endangered Species Act, National Environmental Policy Act, Superfund, and other environmental laws. Restoring and maintaining designated uses and overall physical, chemical, and biological integrity of water bodies requires quantifying the effects of explanatory variables on the response variable. The class of statistical models used to evaluate cause and effect is that of regression. There are linear and nonlinear regression models, including logistic models for biotic data and less widely known regression types such as quantile regression. Linear regressions are commonly applied to environmental, chemical, and biological data. For example, species-habitat relationships of greater sage-grouse or Lahontan cutthroat trout. Applying the correct type of regression model to the available data and the concern to be addressed provides strong justification for policy, regulatory, and operational decisions. The generalized regression model, y equals alpha plus beta x, is a straight line relating the response variable y on the vertical axis to the explanatory variable x on the horizontal axis. The constant alpha is the y-intercept, that is, the predicted response variable value when the explanatory variable is 0. And the constant beta is the slope of the line that represents the mean or average population size for a given habitat size. Every environmental data set has multiple response variables on the y-axis for each value of the explanatory variable on the x-axis. Quantifying this cloud of variability tells us how much of our data are explained by the regression line and how much uncertainty would be predictions of future values. When there are abundant data, A single regression line representing the mean response across the range of explanatory variables provides limited information. It is better to apply a quantile regression that describes relationships of various response variable percentages to the range of explanatory variables. This figure shows the relationship of Lahontan cutthroat trout densities, the y variable, as a function of the ratio of stream width to stream depth, the x variable, over 7 years and 13 streams. Notice the different slopes of the two regression lines. As the relationship of stream width to depth increases, the highest 10% of the response variable decreases more quickly than does the average response. The mean response line is almost flat, while the higher percentiles of fish density decreased with increasing width to depth ratios, and the lower percentiles increased with increasing width to depth profiles. This analysis shows that basing policy or regulatory decisions on a single mean regression line will not necessarily reflect reality. Quantile regressions have also been used to quantify ranges of biotic responses to arsenic in soils and greater sage grouse to habitat densities. Regression models allow us to forecast future conditions by applying the regression equation to a future explanatory variable. The R-squared value represents the amount of response variable explained by the regression model, the equation. We can apply multivariate regression models to accommodate multiple explanatory variables. How much each explanatory variable contributes to the response variable is quantified. There is also the more familiar time series approach to analyzing change over time and predicting future values. Environmental data tend to behave unequally and tend to have unequally spaced collection events. Many time series models assume equally spaced data, and they produce incorrect results with environmental data. There are many suitable models for time series analysis of environmental data. Time series analyses extend past plotting the data. Seasonal trends need to be removed before any overall trend can be determined, and multiple time series can be compared to determine both how and why they differ or are similar. There is another aspect of environmental data that is a comparatively new concept, that measurements and observations of environmental chemistry and biota are components of the whole and not the complete set of chemicals or species. When fish populations are estimated as an aquatic life beneficial use, only some of the species and individuals present are counted. It's the same when benthic macroinvertebrate populations living on the bottom of streams, rivers, ponds, lakes, reservoirs, and pit lakes are surveyed. Geochemicals are most frequently found as multi-chemical compounds, not free ions, and represent only a portion of the whole chemical composition of the water sample. This is particularly important to consider when water quality concerns are focused on toxic metals and organic compounds. While compositional data was recognized early in the last century, it was not until mathematical geochemists took advantage of the work and developed the statistical models that provide the proper way to look at geochemical, biological, and public data to produce more realistic results. Biotic surveys such as those common under the ESA and in species-habitat relationships also benefit by being analyzed as components of a larger whole. Using these models quantifies the spatial and temporal variation in the ratios of the components, resulting in mathematically and ecologically sound insights into the dynamics of the organisms and the ecosystems in which they live. Analyzing analyzing the function, energy transfer, and nutrient cycling of aquatic macroinvertebrate communities as compositions is more reliable and accurate than our structural comparisons based on taxonomic identification, and provides a robust alternative to chemical maximum concentration limits as a method of setting water quality standards for aquatic life. This is a powerful tool for developing policy and regulations because it permits separation of anthropogenic changes from inherent variability of ecosystems. Too many environmental policy and regulatory decisions are based on the output of deterministic models. These models assume that we know the behaviors and that they are relatively static. Ecologists know that this is not the case. Natural ecosystems change constantly and at different scales. Most importantly is that these models do not provide answers to the questions that environmental data are supposed to answer. Statistical models can answer these questions. For example, what is the current status of ambient conditions in a water body relative to its designated uses? How variable are these environmental values over time? How can we separate anthropogenic effects from inherent natural variability? And what future ambient conditions can we forecast, and how much uncertainty is there in our estimates? Fixed equation deterministic models of natural ecosystems also require many input variables and have rates and constants that need to be estimated, assumed, or approximated. These factors make them vulnerable to challenge by project opponents or regulators. Because of the complexities of deterministic models and the large amounts of data required, they take a lot of time, effort, and money to yield results. While state-of-the-art 40 to 50 years ago, they are not appropriate for informing environmental policies and regulations today. Deterministic equation models are effective with static systems such as buildings and bridges, but not with highly variable systems such as the natural world. Statistical models are based on probability distributions, each of which assumes certain data characteristics. There are many probability distributions whose assumptions are met with data from specific environments. This makes the choice of statistical models and the analytical process both technically sound and legally defensible. Statistical paradigms include analytical models that incorporate variability at different scales in the data and allow separation of anthropogenic from natural changes. Forecasts of future states and tests of reality with those predictions are key to compliance with regulations under the Clean Water, Endangered Species, and National Environmental Policy Acts, as well, among others. While deterministic models define the causal processes for observed effects in their equations, statistical models examine a set of potential explanatory variables, singly and in various combinations, to determine which best fit the available data. Policies and regulations can be justified by technically sound and legally defensible best available science by taking advantage of current knowledge in environmental data analytical methods and our understanding of ecological theory applied to all natural ecosystems. All environmental permits, compliance, and litigation involve your data. When how these data are analyzed and interpreted must be technically sound and legally defensible, contact me.